Hello everyone, welcome back to another video. In this video, I'm going to be talking about the IB Physics, don't tune out just yet, IB Physics Uncertainty Power Rule. And what do I mean by this? Well, this will not be just a sort of rule that is in the IB physics course particularly, but you may find that in studying physics in whatever last couple of years course that you do at your particular high school system, that you need to deal with uncertainties in physical quantities, like when you have a sort of quantity x plus or minus your uncertainty delta x, which you don't know. And this uncertainty power rule states that when you have a particular uncertainty of a quantity, or a percentage uncertainty of a quantity, which is equivalent to a fractional uncertainty, delta x over x, where delta x is your absolute uncertainty, so like if it was 3 plus or minus 1 meters, then delta x would be 1 meter, and x would be 3 meters, and your uncertainty would be a third, or 0.33. If this was your fractional uncertainty for some quantity x, and you were taking, say, the cube root of x, where x is that 3 plus or minus 1 meters, how would you go about this? Well, the rule states that since this is equivalent to raising x to the power of 1/3, we take this 1/3 and we multiply it by the fractional uncertainty, delta x over x, to get our final answer for the uncertainty. And in this case it would be 1/9. But how do we make this sort of quantum leap? How can we be sure that this calculation, multiplying the fractional uncertainty by the power here, how can we be sure that it's accurate? Well, I'll let you in on something. It's not. It's not accurate to reality, but it is such a good approximation in the vast majority of cases that there is no, there's pretty much no reason to do anything else. And especially because what you're calculating here is on uncertainty. You already have something that you're not sure of, some point on the number line, and it's within these bounds, right? Could be anywhere. Here, here, here. So why do you need to be so precisely sure of where the bounds end if you're just looking for a number that is within those bounds somewhere? It might not be important at all where the bounds end, because it could be at the other side, or it could be in the middle, or something like that. So this way of calculating uncertainties is fundamentally flawed in a way that doesn't matter to anyone making practical use of it. And I will explain in this video how that works. So, say you have some quantity. I'm just going to get rid of this now since I've brutally mauled this title page. I cannot stand to see it anymore. Yeah, say you have some quantity that you've just measured from your experiment. It's like 40 plus or minus 2 kilograms. So say you're weighing like a small child or something in a terrible and inaccurate scale, like a foot scale, one of these things, where you'd have the dial inside and it would spin. Anyway, say you were weighing this child and your end result is that you find the nominal weight of the child to be 40 kilograms and you have an uncertainty of 2 kilograms in that weight. Let's let this be, or sorry, it's a mass, not a weight. To be pedantic, it's a mass. So you're trying to find the mass of this child, and your mass ends up being 40 plus or minus 2 kilograms. And say you're applying some formula that needs you to use the square of the mass, m squared, for some reason or another. I don't have any formula off the top of my head that would do this, or would require this, but for the sake of argument, say that's the case. Now fundamentally, what this plus or minus sign means is that the minimum value of m that we could possibly have from our measurement is 38 kilograms. That's the smallest real mass of the child that could possibly exist. And on the other hand, the plus sign here means that the highest possible value for the mass of the child that could exist in the real world is 42 kilograms. And with this plus or minus comes a bold claim that any value outside of these bounds could not possibly be the real mass of the child, simply because you know it to be true from your experimental work. So say you have a scale that's accurate to 1 gram, and the child is 40 kilograms to an accuracy of 1 gram. There is no way the child will be 41 kilograms in reality unless you have made some sort of error in your experiment, in designing your experimental procedure, because that would mean the equipment is off by a larger uncertainty than advertised, basically. And you simply can't do physics without good measurements. Right? So you have this consideration that it could be 38 to 42 kilograms, and when you square it, you want to convert this to some other form where you're taking into account that range. So at the minimum, m squared could be 38 squared, which would lead us to, if I am thinking correctly, let's see, 30 squared plus 2 times 8 times 30 plus 8 squared, or 40 squared. It's more appropriate actually to work this out as 40 minus 2 squared, because that's like sort of the uncertainty that we're dealing with. So it's 40 minus 2 squared, which is 40 squared minus 2 times 40 times 2 plus minus 2 squared, which is 1600 minus 160 plus 4, or this sums to about 1404. Right? So that's the smallest possible value of m squared. And now we find the largest possible value of m squared, 42 squared. So it's 40 plus 2 squared, which I think goes to, by the same logic, is equal to 1600 plus 160 plus 4, which is 1764. Right, so now you have some center value, which is, in our case, 1584, between the two extremes here. And that's what our mean would be if we were pulling out all the stops and trying to calculate the uncertainty, like the possible value for m squared, to a ridiculous degree of accuracy, as ridiculous a degree of accuracy as possible. Hang on, no, sorry. This is the number in the middle would be 1604. And this is 1444. Anyhow, you've got this number in the middle, which is approximately 40 squared, and plus or minus 160, basically. And you may notice that this is similar to the equations that we worked out here in our working for actually determining the upper and lower bounds to this quantity squared. So how does that link back into our power rule thing? So basically, if you have learned the sort of binomial expansion that you would have learned in perhaps year 11, year 12, something like that, then a fun exercise to do here is you have this quantity 40 plus or minus 2. You divide, or x plus or minus delta x, let's say, for an arbitrary quantity that we're working with here. And you want to figure out what this sort of rule for percentage uncertainty when raised to a power n is. So what you can do here is, for this quantity, you can divide both sides by x, so you have 1 plus or minus delta x over x. This is sort of the proportion that you're working with. And if you raise this to the power of n, you will find that it's 1 plus or minus n delta x over x, and then plus n minus 1 over 2 delta x over x squared. And now consider the following. Why do I put a plus or minus here and just a plus sign here? Well, that's because this term, this delta x over x, is really the plus or minus delta x over x from our original expression inside the brackets. So when we're just dealing with one of these terms, as in this case, the plus or minus gets multiplied by the plus sign here to become a plus or minus. It's easy if you think about it in the case that's like 1 times plus or minus 1 can be positive 1 or negative 1. So therefore it's plus or minus 1, right? You feel? You get me? So in this second term, because you're having this term be squared, the plus delta x over x squared and the minus delta x over x squared both lead to the same result, because squaring a negative number gets you equal to the square of the positive version of that number, i.e. plus or minus x squared is always x squared. That's in fact how we solve quadratic equations, right? So if we continue going along with our binomial expansion, which we would have learned the formula from in our math class of some kind, then if you go to the third term, you see another plus or minus multiplied by delta x over x cubed. Now, the thing is, IB physics makes us think that the only terms we need to deal with are these ones here. And to be honest, in most cases, it's absolutely correct. Because if you're multiplying to the power of 2, like n is the power of 2. And you've got this term here, which is sort of the n times n plus 1, n times n minus 1 divided by 2 factorial, so it's like 2 times 1 over 2 times delta x over x squared. Usually, delta x over x in any sort of decent experiment will probably be something like 0.05 or less. And that's actually the example value we're using here in our 40 plus or minus 2 kilograms with an atrocious weighing scale, and a terrible weighing scale. The percentage uncertainty, or fractional uncertainty, is still less than 0.05. So 0.05 squared, a small decimal squared, will make a really small number. In fact, in this case, it goes to 0.0025 multiplied by 2, or 0.005. That's less than 1 in 1,000 error compared to this term here, this plus or minus 2 times 0.05, so 0.1. This first term constitutes a 10% error. The second term constitutes a 0.5% error. And we're just trying to figure out an approximate amount for what the error actually is. Like, there's a reason you only express uncertainties to 1 or 2 decimal places at the most, because being uncertain in your uncertainty is just, there's no need for it at all when you're dealing with physical quantities in the sort of problem-solving sense that you usually encounter them. If it was a mathematical study of this kind of stuff, then sure, you may want to include all of these terms. But say you get down to the 8th term in this expansion, plus some number of n's on the top divided by 8 factorial times delta x over x to the 8. This quantity would be on the order of like 5 to the 8 times, I don't know, 10 to the minus 16. It would be ridiculously small and impractical to deal with. So, to put this in a more formal mathematical sense, we can actually describe it as taking a limit of delta x over x to 0 of this thing here. We don't go all the way to 0, we go to some small number. And the term for a small number is usually this lowercase epsilon here. We go to some small number, and the only parts of the equation that become significant at all is the 1 plus or minus n delta x over x, or the power times the percentage uncertainty. So, to recap, this is our quantity. This represents the bounds of where our quantity could be in the real world in terms of that quantity. So like, the bounds could be 0.9 to 1.1 times our measured value, right? That's what this expression represents. And when you're raising this to a power to multiply by your original quantity, the extra terms in the binomial series that results from that, from here onwards, are usually, not always, but usually so small that it is safe to ignore them. And that is why we end up with an uncertainty power rule where delta x over x becomes n times delta x over x. I hope this video was satisfying for you to watch, and I'm going to leave a final note about notation after this scene. Alright, so I want to talk about notation for a moment. This is a sort of footnote to the video you just watched. The percentage uncertainty, represented as delta x over x, is only done so because usually, as a result of the way most sort of measurements in physics works, this delta x can be of quite a reasonable size compared to your measured value x. For instance, you may weigh a mass of, well, usually mass is not the best example. You may take a time, and because of human error, your delta t would be something like 0.3 seconds, the human reaction time, for a time of like maybe 5 seconds if you were forced into an experimental situation where this is your result. And the reason you use a capital Greek delta here is because the change you're dealing with is quite large. And as a fun trivia fact, this delta on my channel thumbnails actually represents all the physics videos, which you'll be receiving more of from here on. But the thing is, sometimes we can also deal with idealized situations. And when the changes in quantities or uncertainties in quantities are really small in these idealized situations, like say you manage to get a perfect experiment where you're measuring something with a light gate and a computer, and you have a t of 34 seconds plus or minus, say, 0.01 seconds for the computer's processing time of the measurement. This capital delta, while still often used, can appropriately be replaced with its lowercase Greek delta, or you may also recognize this as the maths logo of the channel. Because in maths you often get to work with these more idealized cases, like that video about the percentage change in a circle's area. So, in some physics problems, you may see the fractional or percentage uncertainty, delta x over x, be expressed as lowercase delta x over x. And yeah, that's the difference between this capital delta, which I'll be using for my physics videos, and lowercase delta, which I'll be using for my maths videos. And finally, as another note, this English Roman d by dx, why do we use a Roman alphabet d instead of a lowercase Greek delta? Well, that's because even with this delta, this uncertainty we're dealing with here, the change is still finite small number. But when we're dealing mathematically with these differentials and integrals and so on, we talk about taking infinitesimally small changes in y and x, like dy or dx. The smallness of these numbers is infinite. They go to 0. They are 0. And that's why this d is separate from a lowercase delta, because this could still be representative of a physical quantity and its uncertainty. But this is an idealized case, which for mathematical sort of consistency is separate from this because it's actually 0. The value of dx is 0, and the value of dy is 0. It's only when dividing these quote-unquote zeros together that you get a larger number, like the differential of a function, for instance. So I hope that was a interesting sort of epilogue to the video you just watched, and I'll be trying to make a more consistent upload schedule, that is every Sunday, from here on out, and I thank you for watching.